Okay, for this question, it asks you, it tells you the two substitution products are formed, and they're asking what the relationship would be with each other. So let's go ahead and write the mechanism for this molecule. So we have a chiral center that is attached to the CH3, and then we have the leaving group, the chloride. Since this is a secondary halide plus a weak nucleophile, the mechanism must be SN1, because weak nucleophiles can only undergo SN1. So that means the first step of this mechanism is to lose the chloride, or break the carbon-chlorine bond, and then that will leave me with, nothing happens to this chiral center with the methyl, but now I end up with a carbocation here. And my hydrogen is basically straight out. So these three bonds are in the plane of the screen. So now what I'm going to do is now I'm going to have the CH3, CH2, OH group come in and add, and it's going to add 50% from the top, or above the plane of the ring, and it's going to add 50% below the plane of the ring. And that's because for this carbocation, the empty p orbital goes above and below the plane. So as the nucleophile is going to add 50% above, 50% below. And what that means then is that the first product that I'm going to get will have this, the oxonium ion will be above the plane of the ring because it added from above the plane of the ring, and the other product will have the oxonium ion having added from below the plane of the ring, and the hydrogen will be on the bold wedge. So I'm going to get 50% of this product and 50% of this product from having the ethanol add 50% above, 50% below. So the final products then, when I lose my H plus in both cases and give the pair of electrons back to the oxygen, I'm going to end up with these two products. One where the OCH2CH3 group is above the plane of the ring, and the other where the OCH2CH3 group is below the plane of the ring. Okay, now that sets up the answer to the final answer to the question. Because the final answer to the question is, what's the relationship between these two molecules? Well, this chiral center with the CH3 is the same in both cases, and the chiral center that the OH, or that the OCH2CH3 added to, that is opposite in both of those products, which makes those two molecules diastereomers. Okay, so these are the two products of the reaction. What's their stereochemical relationship? They are diastereomers. Okay, let's look at this problem, which is fairly similar. It again says two substitution products are formed from this reaction. That looks to me like I have a chiral center. So I've got a bromine, I've got a CH3 group on the bold wedge, I've got a CH2CH3 group here, and then behind me I've got a CH2CH2CH3 group. So again, this in this case is a tertiary halide plus a weak nucleophile. Both of these indicate that the mechanism would be SN1. And so the first step is to break the carbon-bromine bond and lose the leaving group. And now my carbon is going to become sp2 hybridized. And there's my empty p orbital. So there's my carbocation. I don't know. I don't remember if I put the plus charge in over here, but I should have. Yes, I did. Okay, so now what's going to happen is the methanol in this case, as the weak nucleophile, is going to add to the top lobe. The methanol is also then going to add from the bottom lobe, and it's going to add 50-50 to both cases. So that means where it adds to the top, I'm going to end up with the oxonium ion. Then the propyl group, and I'm just going to abbreviate this as a prop, with my CH3, and with my ethyl group, I'm going to end up with that molecule. And when the CH3 OH adds underneath, from underneath, I'm going to have this oxonium ion with the ethyl group, the CH3, and then the propyl group on the dashed wedge. And the final step in the mechanism is to break the OH bond and move the pair of electrons and give the pair of electrons back to the oxygen. So my two products that I'm going to make are one where we have the propyl group, the methyl group, and the ethyl group with the OH up here, or sorry, it's not an OH, it's an OCH3. And then the other product is going to have the OCH3 group down here. Then the propyl group on the dashed wedge, on the bold wedge, and then the ethyl group. And what's the relationship between these two molecules? Since there's only one chiral center, they have opposite configurations. Therefore, these are enantiomers. So for problem number 6 here, they're saying that they're going to react these with methanol, and then they're going to determine what the relationship is with the final product. So if we look at the first one here, and let's, instead of writing the mechanism out, let's go to the final product. So what we know is that in each case, we're going to react each one of these molecules with methyl alcohol. Since this is a weak nucleophile, the mechanism is automatically going to be SN1, which means that we're going to go through a carbocation intermediate, and the methanol will add 50-50 to each of the two lobes of the carbocation. So that means that this molecule is going to lose the Br minus. I'm going to end up with that carbocation with its empty p orbital, and when the methanol reacts with it, I'm going to end up with the OCH3 being on a dashed wedge because it will have reacted from this direction, and if it reacts from the front of the molecule, I'm going to end up with the OCH3 on the bold wedge, because it will have reacted from the front. So in other words, we can write this molecule where we simply take the OCH3 molecule and we put it on a dashed wedge and the bold wedge. In this case, these two, since there's a single chiral center, these are going to be enantiomers. This problem is exactly like what we just did. It's got a propyl, an ethyl, and a methyl group. So when we react it with CH3OH, if we want to jump right to writing the final product, just simply add the OCH3 group to the dashed wedge and add the OCH3 group then to the bold wedge. These two, again, there's a single chiral center. These have opposite configurations. They're going to be enantiomers as well. Okay, for the cyclohexane, I'll put this hydrogen in. We're going to lose the carbon-bromine bond. What you can see here is that we're going to end up with the chiral carbon, or we're going to end up with a carbocation. Sorry, it's actually not chiral. And when the CH3OH adds to both the top and the bottom faces, we're going to end up with the OCH3 on the bold wedge. We're going to end up with the OCH3 on the dashed wedge. And the only question here is this a chiral center? Is this a chiral center? And the answer is no. And so this is going to be an achiral compound, because basically this group and this group are the same, those two are the same, those two groups are the same, and we end up in the same place. So those molecules do not have a chiral center. And then the final molecule looks like this. So when the carbon loses its bromine, when the carbon-bromine bond breaks and I make the carbocation, I'm going to add the OCH3 of the methanol. Now I'm going to put this hydrogen in just to show you. Then what will happen is, in one case, the OCH3 will replace the bromine in essence. And for the other molecule, the OCH3 group will be on the dashed wedge, so that again we're again basically making both enantiomer, or both chiral centers, both orientations of that chiral center. Now in this case, because I had a chiral center already in the molecule and it didn't change, then these two chiral carbons are the same in these two products. These two are opposite because that's where the SN1 reaction occurred, and I got a 50-50 mixture of chiral centers. In this case, these are going to be diastereomers.